AP Calculus AB, Unit 9, Day 1. So this is our first lesson of the new unit, and we're going to be working off of what we were doing last unit with integrals, and we're going to be doing a lot more definite integrals this unit, but we're also going to start to estimate them, okay? And I mentioned this a little bit at the beginning of last unit, but we didn't really do anything else with it. So when we slice things up, a lot of times they're going to be equal widths, but not all the time. And, we could take a quick look at this problem on the back that we're going to do. And this is a free response problem. And so right away, when you see a table on a free response problem, you're going to be doing estimates. Like, you're not going to have a function. You just have a snapshot of some of the values, and you can kind of get some rough answers with those. And so if you look further down, it says, part C, it says the average temperature of water in the tub is, and so we're going to try and integrate W. And that means, one way to interpret that is by finding the area under the curve. We use the left Riemann sum with 4 subintervals based off of what's given here. You can see it's 1, 2, 3, 4 subintervals. So anyways, we'll come back to that later, but let's look at the different ways that we can estimate the area under curve. So these ones are all going to be rectangular approximations. And so we're literally drawing rectangles. If we do a left in, that means we use the left side to be the height of the rectangle. And we find the area of each of those. And so here, the bases are the distances between the edges of each slice. And then you have the heights right here, which I'm just giving you those values. And so left in point Riemann sum, LE for short. It's an approximation, so it's really appropriate to use this symbol. It's not like a rounded, it's a rough answer. And so you should show the work. 3 times 8 plus 2 times 12 plus 3 times 13. And this is work that you would need to show on a free response question to get full credit. Now after that, we're going to say, okay, well, that's 24, and that's 24, and that's 39. And if we add these all up, 8, 17, carry the 1 to 7 is 8. So then we could say our final answer is the integral of f of x from 1 to 9 is approximately 87. Now, if you look at this graph, is this over or under approximation? This is an under approximation. It's for sure less than the real area because each of these slices is below the curve, right? We'll get into that later. Okay, next one is a right end approximation. So that means we're using the right side to create each rectangle, which means the left side of this first one never even gets used. Okay, so we're using the right side, and we're going to obviously get a different answer. The bases are the same. The heights at each slice are the same, but it's just which side we're using. So I find it sometimes, good to maybe label these values next to it, because you're not going to actually have a graph when you do this approach. You're going to read these values from a table, and I would recommend drawing a picture. So let's show the work. Base times height, base times height, base times height, and we get 36 plus 26 plus 51. Do a little work here, vertical addition, 12, 13, add 1 to 10 is 11. So the integral from 1 to 9 of f of x, it's the same function we're estimating, but with this approach we get 113. And this is obviously an overestimate. It's more than the actual value. All these rectangles, all this extra area, that's error, And now there's another method called midpoint Riemann sum. So Riemann sum means rectangle, so these are all Riemann sums. So midpoint says, okay, for your slice, so we're using the same slices, the same heights on each side, but this time we're going to take the halfway point whatever the function is there and make that the height of a rectangle, right? So I'm taking the halfway point in between the left and right edges and saying, let's use that height of the function. Now, what you might notice is like you get a little over and a little under error. So this one seems better than these other ones, right? This one's probably closer to the actual value. And I'd say, yeah, that's probably true. Now, you got the one thing that's hard about this is you got to figure out what x coordinate is right in the middle. So in the middle of 1 and 4, that's 3, half of that's 1.5 would be 2.5, right? Half of this distance is 2, so this is going to be 5. This is 3, half of its distance is 1/2, so that's going to be 7.5. You add 1/2 to this one or take 1/2 away from this. Those are the x coordinates. Now we're still doing 3 rectangles. That just tells you where to look to get the y value. Now these values I'm just kind of roughly estimating. Let's say this one is like 11. You would never have to guess this, but just for this example, you could say this one's like 12.5, and this one is like 14. So I'm going to show the work. Base times height plus base times height plus base times height. And write down what these are: 33, 25, 42. It's 8, that's 10. Carry the 1 to 9 is 10. So this one is 100. Now, all of these were estimating the same exact thing. Got very different answers. This one's probably closer, right? It's got a little, this one's extremely below it. This one's extremely above it. This one's kind of in the middle. And if you look at the values, it also looks like kind of in the middle. It happened to be exactly in the middle, but that's not always going to happen. Now, are these under or over estimates? And if you look at the picture, it's easy to tell. This one, it's harder to tell if it's over or under. It's not perfect. It's closer, but still, like the over and under on each slice isn't perfectly the same. So we got to figure out and be able to predict this without a nice picture. Now, here we'll just do a couple examples. Quadrant 1, it's increasing and it's concave down. So it's going up, it's concave down between 2 points. Okay, if you use a left-end approximation, that is clearly an under approximation, right? You use a right-end, that's clearly an over approximation. So left and right, and that doesn't have to do with concavity. That just has to do with the fact that the graph's going up, right? So this one deals with increasing. That's the only reason. Concavity doesn't matter. Now, midpoint depends on concavity, okay? Because here's the midpoint, and the the over is more than the under, so I would just say from the picture, it's an overestimate. But here's the thing. Anytime it's concave down, a midpoint is going to be over. And the reason is the curve is getting less and less and less steep, right? So it changes more dramatically at the beginning, which gives you more of this over, okay? And I'll show you the next example right at this, that even if it's decreasing concave down, the same thing happens. So this is always going to be over for concave down for midpoint. So let's look at this other one. Left end is for sure going to be over. And I wouldn't even try and memorize these because I would just draw a simple sketch with one slice and it makes it super clear that this is an overestimate, right? Right end for decreasing is going to be under. So this is, if it's decreasing, doesn't matter about concavity. Now concavity is going to affect the midpoint one. So if anything, I would maybe just try and remember that concavity does it. And you can even draw a picture for these ones and you can see that the graph, because the graph is going down and it's concave down, that means we're losing more and more slope, which means it's getting steeper in the negative direction, which means that the over part here is more than the under part. So it's still an overestimate because it's concave down, which is exactly what we said over here. Because it was concave down, it was an overestimate. So it doesn't matter if it's going up or down for midpoints. Left, right end, up or down makes all the difference. Concavity doesn't matter. I would always just draw a quick sketch and not try and memorize it because I feel like I'd probably mess it up. Now, here's one more way of estimating the area. Now, a lot of people would say, oh, well, this one's going to be the best method, right? But that would really, if there's not many slices, then probably, okay? Probably. And these are all increasing curves. So if it's increasing and decreasing, it could change it, you know. But if we go to infinite slices, they're all going to approach the same answer. And that's where calculus comes in. We take it to infinite slices, infinitely thin. Now, trapezoids, we're doing the same graph as we did up there, okay? So the slices are the same, but instead of doing rectangles, we're going to connect the top points on either side of the slice with just a secant line, and it creates a trapezoid. So we get a bunch of trapezoids. And I mean, if you look at this, that's pretty good, right? I mean, that kind of hugs the curve even better, right? This is not called a Riemann sum. Riemann sum is specifically the rectangle ones. This is an estimation technique, but using trapezoids. Now, let's review. What is the area of a trapezoid? I think we reviewed this recently. I wouldn't try and memorize the formula the way you learned it back in like Algebra 2 or Algebra 1 or geometry. To me, a trapezoid, it has one pair of parallel sides, exactly, right? And then what you do is if you cut this in half and you draw a line straight up and down, you could move this little piece up right here and fill it in. And if you do it over here, you're going to get the same thing. This little piece will fill this in nicely. And now you just have like a nice rectangle, perfect rectangle. So really trapezoids are the area of a rectangle. Okay, they're just base times height. The height is the height. The base is the tricky thing. The base is actually the length of this right here, which we call the median. And it's parallel to the bases. It's exactly halfway between them, distance-wise. And it is exactly the average of them. It's just the average of the two bases, which I feel like, yeah, that feels good. I think I can remember that. So when I do the area of trapezoid, I say, okay, well, it's base times height, but we're going to use the average of the bases times the height. It's just a rectangle, base times height, but there's two bases, so you just got to average them. Now, on our trapezoids over here, the bases are vertical. So that's something that's also a little weird, is that we're used to thinking of trapezoids kind of laying on their side like this, but these ones are sideways. The parallel sides are up and down. So the bases are these things, okay? And the height is that these are actually the height of each trapezoid. The 3, the 2, the 3, those are the heights of the trapezoid. That's the distance between the parallel sides. So in our work, we're going to say, okay, average of, we could even write the lengths of the sides or the heights of those on there. Those are going to be our bases. So the first one is going to be average of the bases times the height. And the next one is going to be average of the bases times the height. And the next one is going to be average of the bases times the height. Now, on a free response problem, you have to show this work to get full credit. Even if you get the right numbers, if you don't show the setups and like show them that you're doing trapezoids, you don't have to have a picture. You can draw a picture to help you. That's not going to give you credit. But you need to show this. And again, this is an approximation. So this is going to be 20 over 2 is 10. And this is going to be 25 over 2. I'll just leave it like that, 25 over 2. And this one's 30 over 2, which is 15. And so then we get 30, 25, 45. If we add those up, we get 67, we get 100. So the integral of 1 to 9 of f of x dx is approximately 100. Now, this is the same one we were estimating up above. It's coincidental that it gave us the same value as the midpoint. But trapezoids are probably better than midpoints, a little bit in the short run. But in the long run, if we go to infinity, it really doesn't matter which approach you take. They're all going to approach the same limit, the same answer. So, all right, let's take a look at this free response problem on the back. And, we're going to be doing more and more of these as we get more tools. There's another approach called Simpson's rule that you could check out. Just if you're interested. So going back to this problem, right when you see this free response problem and you see there's a table at the top, you got to be like, I'm going to be doing estimation techniques. Probably going to estimate the slope by connecting 2 points near a point I'm interested in. I'm probably going to do like a Riemann sum, rectangles or trapezoids to find the area under the curve, which I don't have a picture of, but I might do a rough sketch of just to help me organize it. The temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function. Those might come in handy later, where W is measured in degrees Fahrenheit and T is measured in minutes. At time 0, the temperature of the water is 55. So that's initial condition. So W 0 equals 55. We'll probably need that maybe to find a C value or something. The water is heated for 30 minutes, which they don't even show. It shows 0 to 20, but I might put that up there just to put that there. Beginning at time t equals 0, values of Wt at selected times t for the first 20 minutes are given in the table. Use the data in the table to estimate W prime 12. Show the computations that lead to your answer using correct units. Interpret the meaning of your answer in the context of this problem. Which means you better write like a sentence talking about water in a tub and temperature and things like that, not just use generic calculus terms. So if we want to estimate 12, look right here. Here's where 12 is. So we're going to use the closest 2 points and just do rise over run, slope of the secant line, and that should be roughly the derivative of 12. And so we're going to show that work, W prime 12. We're going to label our work, and we're going to say it's approximately W 15 minus W 9 over 15 minus 9. Now this might look familiar. This is also the way that you find the average derivative between 2 points, but that's not what we're trying to do here. Coincidentally, same work, same answer, different interpretation though. So we're going to plug these values in. So you guys show the setup. Now, this is a problem that you would be allowed to use graphing calculator on, but you still got to show the setups. You can't just give me an answer. It said show the computations. Okay, so this is going to be what, 6.1 over 6. And on your calculator, it'd be 1.016 or 1.017, 3 decimal accuracy, rounded or truncated. Then I'm put the units, degrees Fahrenheit per minute, right? The top is temperature, the bottom is time. And so this is our approximation for W prime 12. So that's one part of it. We showed our work, we got our answer, put the units. Now it says we have to, using the correct units, interpret the meaning of your answer in the context of the problem. Now, in general, if you get that the derivative is positive, then you should probably say that something is increasing. If you get that it's negative, you should probably say that something is decreasing. That's probably the most go-to. So in the context of the problem, we got to say the water or the temperature of the water in the tub, context, is increasing at a rate of approximately, this isn't the actual increasing, this is approximately 1.016 degrees Fahrenheit per minute. Okay, that's not enough. You got to be all the time. That's what. No. At time t equals 12, still not enough. Minutes. You got to. You need all of this. Context of the problem, correct units. That's what you need. Now, Going to the point breakdown, these are worth 9 points each. Every free response problem in the AP Calculus A/B test is. This particular one was 2, 2, 3, and 2. So it's good to kind of know where your points are coming from. And they don't give half points. On this problem right here, 1 point was for your answer and your work, and 1 point was for the interpretation. B says, use the data in the table to evaluate 0 to 20 of W prime T dt. Using the correct units, interpret the meaning in the context of the problem. Now here's, I don't know if we've done this a lot, but you guys should know that the antiderivative of W prime, if you're going to integrate W prime, you're going to get W, right? Right? And then you're going to plug the limits in. Top first, bottom second, subtract. And these are values that are just in the table. This is not an estimate. This is exact. These values are in the table. And so we get, what do we get? 16.0 degrees Fahrenheit. Now these are degrees. Those are temperatures, right? So that's your answer. The interpretation is, and this is something we haven't talked a lot about, but anytime you integrate a derivative, you're going to get the total change in the original function between those times. And if you look at this, this is the temperature at 20 minutes minus the temperature at 0 minutes, means that's how much the temperature changed, overall change in the temperature from time 0 to time 20. And that's usually something you would use in your interpretation. So you could say 0 to 20 W prime T dt is the total change in the temperature of the water, context of the water in the tub, units in degrees Fahrenheit. Okay, you got to mention that. From, and now you got to put time, from time t equals 0 to t equals 20, you're going to lose the points if you don't put minutes. If you don't mention the times, you don't put the units, you're going to lose the points. So that was 2 points, probably 1 for the interpretation, 1 for your answer. That has to have work supporting it. Okay, C says 0 to 20, the average temperature of the water in the tub is 1/20. So they're just telling you this is the average temperature in the water. And by the way, this is mean value theorem for functions, and we haven't talked about that quite yet. But we can get away with it, I think, right now without talking about it. They're just telling you, use this, okay? It says use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate the average. Does this approximation overestimate or underestimate the average temperature in the water over these 20 minutes? Explain your reasoning. So you can't just say, oh, it's over or under. You got to say why, which probably has to do with it either increasing, decreasing, concave up, concave down. So we'll just start with this. Now, I would draw a picture of these values, just a rough picture. And this is not going to help me this isn't going to get me any points directly. But I think it'll help me organize my work better. And maybe even probably make a good guess if it's over or under. So I'm just kind of roughly drawing them taller and taller because they are getting bigger and bigger. All right. Okay. And then I put these here because these are going to be bases of my rectangles. And they said a left Riemann sum. So these are rectangles. Left Riemann sums, you use the left side, right? And we're not going to use that one then because we're using all the left sides. The last right side never shows up. So this is really helpful for me. So I'm going to say approximately 1/20. Don't forget the 1/20. I'm going to show my work. Base times height. 4 times 55. You got to show this. You got to show them that you're doing rectangles. 5 times 57.1. 6 times 61.8. 5 times 67.9. Okay, and let's say you make a little mistake here. This is where you usually could get some points. So usually this is 1 point right here. Now we are allowed to use a calculator. So I'm gonna go ahead and jump into that. So this is 1/20. On my calculator, I got 220, 285.5, 370.8, 339.5. Keep all the decimals right now. And then that gives me 1215.8 over 20, which gives me 60.790 degrees Fahrenheit. This is a temperature, okay? If you do the work here, this is temperature times time, but then you're being divided by time. This is the time from 0 to 20. And you're doing average temperature, so it should just be degrees Fahrenheit. Now, it said, is this over or under? Well, remember, it either has to be always increasing, always decreasing, always concave up, always concave down. And you could connect these points just to make a rough graph. And it looks obviously like an under approximation. Now, is it under because it's increasing, decreasing? Is it under because it's concave up or down? I would maybe remember that left and right end depend on increasing, decreasing. Concavity has nothing to do with it. Plus, you don't even know about concavity here. Now, if you're going to say because it's increasing, just because this graph is going up all the time, doesn't mean it's increasing in between. You can't assume that. The only reason we know for sure it's increasing the whole time is because they told us right there. They told us. So we need to mention that. So we're going to say this is an underestimate. An underestimate. Since W is strictly increasing, okay, and that's not enough. We got to mention it's not just because anytime you have an increasing function doesn't mean you're going to underestimate. It's the combination of a strictly increasing function with a left endpoint Riemann sum. You have to say both of those things to get this point. So you have to say this is worth 1 point right here. If anything's missing, you lose that point. So we get the setup's a point, the answer is a point, and then the over-under with explanation is a point. Okay? Now, let's see. D says for 2025, function W that models the temperature has first derivative. So they're saying, oh, for some of the time that they didn't even give you anything for in the table, they're going to give you the derivative. W prime at t equals 0.4. So they're actually giving us an equation now for the derivative. Okay. It says, based on the model, what is the temperature of the water at 25? So they want to know the temperature, which we should use W for. They want to know the temperature at 25. Now this is going to get a little out of our abilities right now. I'm going to probably be teaching this to you very soon. You know, if you want the original function, don't we usually say, oh, well, it's going to be the integral of the derivative, right? Okay, the only problem is we can't integrate this. Okay, we can't. And, but we do know that if we integrate W prime, we get W, right? And if we had a definite integral, we could plug the endpoints in afterwards, right? Now here's the deal, we want 25, so let's put 25 as one of the endpoints because then we'll get W25 in our work. But we also need another W that we know the answer to. And we should use the 20 because that's where this derivative starts, is 20. So here's the interesting thing is we're going to integrate the derivative to get the original function, plug limits in. We want one limits to be the one we're looking for. We want one limits to be one that we know. And we can't just use any one on this one. We have to use 20 because that's when this derivative starts being true. We can't integrate this by hand, but we can integrate it on a calculator. A calculator can integrate any of these, okay? It doesn't even use calculus rules, by the way. It actually uses estimation techniques. It uses like rectangles. So if we do this, we can get W25 because W20, if we look in the table, is 71.1. So we're almost there. W25 is going to equal 71.0 plus this integral of the derivative. Now, another way to think of this that we're going to get into more deeply later that would make this technique also just make more sense. Like, I think it should make sense based off of what we already know. But also, if you think, if this is the derivative, these are the changes in the temperature. So if we take the temperature at 20 and then we calculate, if we add all the changes in the temperature up from 2025 and add it here, that should give us what our current temperature is. So I'm going to do on my calculator. We could do this all at once, or you could do it two separate, calculations. But we could do it all at once. 71 plus, on the home screen we can. Math 9.4 square root of x cosine of 0.06x. We better be in radian mode with that trig in here. Okay, so that's that, comma x, comma 20, comma 25. And there's the answer, 73.043. And this is degrees Fahrenheit because this is a temperature. And this is actually an exact answer. That derivative was exact. Points on this, there's 2 points. So probably 1 point for the answer and 1 point for having integrated the derivative or something like that, usually. Anyways, we'll use that technique more in the future. So that's what we got. Plus, by the way, even if you could do this one by hand, which you can't, but even if you could and you had a graphing calculator, this is way faster than the finding plus C, because that's what the W20 would be, is that it would help us find WC, or find the C value, and then we'd write the function, then we'd plug 25 back in. That's just a lot of extra work. And having to integrate something by hand and not mess it up, work, possible mistakes. Use your calculator whenever you can. Whenever they give you a calculator, use it to do the calculus. But you got to show your setup still to get full credit. Try the homework tonight, 9-1. All the subdivisions today are going to have equal subdivisions. In fact, maybe I'll try and give you a little quick heads up on, maybe we could try a couple real quick, so that, I don't know, because, okay, the first one, you're just kind of drawing pictures, just drawing pictures and, sketch the picture, illustrate it. You're not actually finding any number values. These ones, you have this table right here that's being used for all of these problems. Now, what we have to do, for instance, like on this one, it says use the left in LE with 2 subintervals. We got to use, and we're estimating this for each of them, okay? So I would draw pictures for these. I'd say, okay, well, we're going from 1 to 13, but we're just going to do 2 subintervals. So what would this x value be if they're equal? Well, I would find this distance. I would cut it in half. I get 6 and add that to the bottom or subtract from the top. And then you're going to look up these values here. So this is 7, and then 7 is at 6, and then 15 or 13 is at 1. And we're doing left in, so we're doing the left side. And so we're not going to actually end up using this one. I would draw that, and then the work should be easy. 1 to 13 f of x dx is approximately, the bases are equal, 6 times 7 plus 6 times 7. I want to see the work, just like a free response problem would require. And so that's going to be 42 plus 36, so that's going to be 78. So the integral from 1 to 13 of f of x dx is approximately 78. So that's what you're doing on all these, okay? I would draw little pictures, and you're trying to pull certain values out of this table for different problems. 3 subintervals, the slices are going to be different places. 6, different places. You got trapezoids, midpoints, okay? The midpoint ones, you're going to, so this one's going to look just like this, except that you're going to need to find the points in the middle to make your heights for those, okay? On the back, this says, this is a little different. It says create a table of values to estimate it. So we're going to make our own table of values because we actually have the function for part A, and we're going to estimate it. And then part B, we're going to find the exact answer, just as a nice comparison. Excuse me. So if we're doing left in with 2 subintervals, we can make a little table. And we're starting at A, okay, A to B, and we're doing equal width slices. So this is 6, so we'd go here, 6, add 3 or subtract 3. Now we're going to plug these into the original function. So we're going to get 9, 36, 81. And then I would draw a quick picture. And so we're doing 3, 6, 9. We have 9, 36, 81. We're doing left in, so we're using the left sides only, so we're not even going to use that guy. And then I would show you work. So we're integrating from 3 to 9 of x squared dx, and that's approximately base is 3 times height is 9, plus base is 3, height is 36. And so we get 27 plus 108. And so our answer is going to be 135. So the interval of 3 to 9 of x squared dx with the left end mean point, the 2 slices, is about 135. Now, the exact answer is we're going to actually integrate 3 to 9 of x squared dx. So we started doing this last chapter. We find the antiderivative, power rule, plug the limits in, top first, bottom second. So 9 times 9 times 9 over 3. I'm just going to leave it like that. Minus 3 times 3 times 3 over 3. So 3's cancel. One of those 3's cancels. So that's 81 times 3 is 243 minus 9. And so the exact answer, 3 to 9 of x squared dx, is 234. That's the exact answer. So that's what you're doing on each of these. You're going to set up a table, do an estimate, and then you're going to actually find the exact. So this is an estimate, and that's why I use this symbol. This is exact, and that's why I use this symbol. Okay, so that's what you're going to do on those. And at the bottom, you're going to try and decide which ones are increasing, decreasing, or which ones are over or under estimates. And I would just draw little pictures to help with those. So, all right, go for it. Try the problems yourself.